An inductor looks simple from the outside, just a coil of wire. But inside that coil hides one of the most powerful principles in electrical engineering. When current flows through a conductor, it creates a magnetic field. And when that conductor is wound into a coil, the magnetic field becomes concentrated and stronger. That is the basic idea behind an inductor. It stores energy, not in electric charge like a capacitor, but in a magnetic field. The moment current starts changing, the inductor resists that change. This behavior comes directly from Faraday's law of electromagnetic induction, discovered by Michael Faraday, which states that a changing magnetic field induces a voltage. In practical terms, the voltage across an inductor is given by the equation V equals L multiplied by dI over dt, meaning the faster the current changes, the larger the induced voltage becomes. That is why inductors oppose sudden changes in current. If you suddenly try to increase the current, the inductor pushes back. If you try to suddenly stop the current, it generates a high voltage spike to keep the current flowing. This property is known as inductance, measured in henries, named after Joseph Henry. Now think about real-world applications. In power supplies, inductors smooth out ripple currents. In DC to DC converters, they store and release energy rapidly to step voltage up or down efficiently. In radio circuits, they work with capacitors to create tuned resonant frequencies. In transformers, which are essentially coupled inductors, magnetic fields transfer energy between coils without direct electrical connection. When you add a core material like ferrite or laminated silicon steel inside the coil, the inductance increases because the magnetic permeability improves, allowing stronger magnetic flux for the same current. But there is also a limit. If too much current flows, the core saturates, and the inductance suddenly drops, which can damage circuits. That is why engineers carefully calculate inductance using the formula L equals mun squared A divided by L, where mu represents permeability, N is number of turns, A is cross-sectional area, and L is magnetic path length. Inductors also introduce reactance in AC circuits, given by XL equals 2 PIFL, meaning higher frequency signals face higher opposition. That is why inductors block high-frequency noise while allowing low-frequency or DC components to pass. You will find them inside switch-mode power supplies, motor drives, EMI filters, wireless charging systems, and even smartphone circuits. That small spiral of wire is one of the fundamental building blocks of modern electronics, proving that even the simplest component can hide deep physical principles that power our entire electrical world.